So hello everyone, this is lecture 16, the last lecture, the 15th one. We studied about the 1D monoatomic lattice vibrations. Okay, we derived the formula for the dispersion relation we derived actually for the particle which is vibrating, and the general formula. We find the expression for omega in terms of k, and that is called the dispersion relation. Okay, this was the relation we got, and when we solved it more, then we get the formula in form of this 2 Vs by a sine ka by 2. Then we take some cases in which the long wavelength region k tends to 0. Then we found this result omega equal to Vsk. Then we take the short wavelength result. Then we found something like this: Vp and Vg were different, and we got a dispersive medium. And for the long wavelength region, we got the non-dispersive medium because both were coming the same, Vp equal to Vg. And then we discussed the cutoff frequency, means the maximum frequency possible in a 1D monatomic lattice. Now here it ends, the monatomic lattice. So there are some questions you need to do. Okay, first you try. In the next lecture I will give some solutions. Well, most of the questions we already did actually. So just like read the first question. For 1D monatomic lattice, find the density of states and plot rho omega versus omega. So we need to find the density of states. So how do we find the density of state in 1D? So we know the formula. Actually, we derived previously for the density of state, that was gk dk equal to L by pi dk. That was the formula. So here let me give you the solution. So we have this relation. Now what we need to do is just find a value of dk in terms of d omega. Okay, so from here dk will be, just to differentiate it, we will get sine, there will be cos k by 2, and a by 2 will be out, so we'll get something like this. So dk will be this, and here cos k by 2 can be written as 1 minus sine square k by 2, and we know what is sine k by 2, that is omega by omega m. So we'll get this relation in terms of dk in terms of d omega, that is this. Now we know that what is the density of states, that will be g omega d omega equal to L by pi dk. So L by pi dk value is this, substitute here, and this will be our number of states. This is number of states. Now take the d omega this side, we'll get the density. So this will be the number density. Now in the question it was asked to plot the curve. So we can plot omega and omega. Like when omega is 0, what will we get? We'll get the maximum value. Not the maximum value, we'll get something like 2L by pi a omega m. So that will be this for omega equal to 0. But when omega equal to omega m means at the maximum omega, the possible, the cutoff frequency, then we'll see that rho omega will tends to infinity. So the curve will be like this. This is just mathematical. Now if we need to understand its significance, then what is this? Means when the frequency is increasing, then the number density is going to infinity, means at the omega m the number density will be infinite. So if we see it in this way, like for the first mode, that was 1, the 2, the 3, as we see that number lines coming together, means they are coming close. So at very high n we'll have a lot of number of states with the very minute difference between them, so we will call them like continuous number of states. So at the high frequency we'll get continuous state, most of it's continuous in that way. So that's why we got this type of curve, because at high n we'll get a large number of states, so there will be very minute difference between them, so we'll take them approximately continuous. That's why we get at omega m this tends to infinity. If you get I hope you get the question. There are some more questions. So for the same, for 1D monatomic lattice, find the density of states and plot omega in the long wavelength region. So what will you do here? In the long wavelength region, we derived this formula, omega equal to Vsk. Use this and find the density of states. So you can do that. We already did in the previous questions I gave you. Now the same for 2D, find the density of states in long wavelength region. For 2D, what will you get the number of states formula? So that will be just like it's gk dk equal to L by pi dk. So for the 2D, we know the formula, that was this. For 2D you will get this formula, 2 pi k dk. And for 3D you will get this formula. Okay, so you just apply, find the relation dk in d omega and just substitute and you will get the answer. Okay, same for the 3D you will find. Okay, so let's just see this question, the fourth question. For 3D, same as 3. So okay, in the third question you can't use the same formula, means for 1D you can use that formula omega equal to vsk for the long wavelength reason, but in the third question it was asked for the 2D. Then for 2D we find this equation for the motion, m omega square equal to 2 beta, this. So need to solve this question. Okay, and in the fourth question it was asked for the 3D. So I will show you the solution for 3D. You will try the same for the 2D. Okay, it's not different, it's just exactly same. So for 3D we have this equation, m omega square equal to this. So we'll use this equation to find the dk and we substitute it in the equation we have for the gk dk equal to L by 2 pi cube 4 pi k square dk. Okay, so let's just see the question number 4th. So we have this equation. Now we need to solve this for the long wavelength reason. If lambda is very long, then k tends to 0. K tends to 0. If k is very small, then we know that what is the formula of cos theta? That is 1 minus theta square by 2 factorial plus theta 4 by 4 factorial, and series will go on. So for the small theta, we know that it can be limited to 1 minus theta square by 2 factorial. We'll get the correct result. So we can write cos kx a is equal to, is approximately equal to 1 minus kx a square divided by 2, just from this formula. So we'll substitute here for all cos kx a, cos ky a, cos kz a. Then we will get something like this. Cos kx a will be this, cos ky will be this, cos kz will be this. Now when you substitute it in this, then 1 1 1 you will get 3, and then plus plus all these plus kx square a plus ky square a plus kz square a. Then you will take the a square by 2 common, and then what will you get? You will get just square of kx square plus ky square plus kz square. Then that can be written as k square, k square. So when you solve this, you will get this result, m omega square equal to beta a square k square. From here you will get beta a square k square. Now from here omega can be written as root b beta by m ak. Okay, so now you have the dispersion relation for the 3D. Now you can solve it. D omega will be root beta by a d dk. Okay, so use this relation for 3D, substitute for the dk, and we know that in the 3D cases we multiply by 3 here because of 3 states of polarization. So here it will come out like this, means you can solve it further, and you just take the d omega in the downward side, and then you will get the density and you can plot that. So it's easy, but just you need to know how to solve these. Okay, when you get the dispersion relation, it will be very easy to get the final result. Same for the 2D, you try to solve this equation, put the cos kx equal to the same way 1 minus kx a square divided by 2 factorial, and same ky, then kx square plus ky square will give you k square. Then you will get the relation and you can solve for 2D. For 2D you know the relation we find for the density of states. 2D you will use this. Okay, so that will be easy. Now there is this last question. For 1D monatomic lattice of interatomic separation of A, find Vp and Vg. Plot Vp and Vg on the same graph in the region. So we need to find or plot the Vp and Vg with k in the region of minus 2 pi a, 2 pi a. Okay, so 1D monatomic lattice, we know what are the relations we got for the Vp Vg. You have the formula, that are these: Vp equal to Vs sin k by 2 ka by 2, Vg equal to Vs cos ka by 2. So these were the relations. So if you need to plot them, then how will you get? Let me show you the graph. So these were the relations, Vp equal to this. If you need to plot the sin x by x curve, like y equal to sin x by x, you will get this type of curve. This will go down. So here also you are getting the same type of curve. So if you plot Vp here on the y-axis and k on the x-axis, then for the k tends to 0, means when sin 0 by 0, what will you get? You will get equal to 1. This term will be 1. So you will get Vs. Vp will be Vs. So at k equal to 0, we get Vp equal to Vs. And if we see from the Vg, then at k equal to 0, we get the Vs. So when it is in this area, we get the same result for Vp and Vg. And we already proved that because of the non-dispersive medium, when k tends to 0, or the long wavelength region, we call that. Okay. But it differ with the moving towards or backwards k. Like so when this term will be 0, this term will be 0 when k by 2 will be n pi. So it will turn out to be 2n pi by a, 2n pi by a. So first 0 will be 2 pi by a for the Vp curve. And the negative side will be at minus 2 pi by a. So we'll get something like this curve for Vs, Vp. Okay, in this area, minus 2 pi a to 2 pi a. Now for Vg, we found at the maximum value at k equal to 0, it will be Vs. Now when it will be 0, when k by 2 equal to n plus 1 pi by 2, n plus 1 pi by 2. So we'll get from here that it will be 0. Oh, it will be 0 at minus pi by a. And you can make the other also by putting the n value. But only we need to find the curve between minus 2 pi and 2 pi a. So it will be at minus pi by a. So we find Vg curve will be like this. So we get this type of curve between minus 2 pi and 2 pi a for Bg and Vp. So you can just see this graph, and you can see that for 0 they are coming together, but when we are going far, they are just separating. So have you get? Here our topic is completed for the monatomic lattice. Now today we will study the lattice vibration of 1D diatomic lattice. Diatomic is simple, means that now we have two type of atoms in a single molecule in a solid. Okay, so see from this curve, like now we have this dot represent 1, which is small m mass, this cross represent capital M mass. They are distributed like this, and this is a state of equilibrium. When they are at the state of equilibrium, no force is acting on this, so it will be in this type of state, no movement. The distance between two masses is capital small a. Okay, we put it as n number, and then this will be n plus 1, n plus 2, this will be n minus 1 and n minus 2. Now we displaced this particle from here, we put some force. So because of this displacement, all particles will getting displaced by a small amount. The amount will be decreasing from this side to here to this side. So we displaced this as this. Okay, so this also displaced, this also displaced, this also displaced. This displacement is decreasing. Now the last particle will be having very less displacement. So we take the snapshot at particle instant, so it will be look like this something. So we need to find equation or the dispersion relation for this kind of system where two atoms are there, that is a diatomic lattice. Okay, in the 1D. So just as we did in the previous one, we found the equation by, we take this as reference point or the reference particle. Now from here we can see there is F1 force is this side, F2 force is this side, and displacement is also this side. So un plus 1 minus un will be displacement. So F1 equal to beta, this is constant, spring constant, or you can call it the force constant. The displacement will be this, so F1 will be beta this, and F2 in this direction, displacement in this direction, so we will get the negative sign, and the displacement will be un minus 1. Now for the nth particle, we have force equal to this, total force on this. Now let's consider the another particle also, because now we have two atoms. This is capital M mass. Now put it F1 prime force like this, F2 prime force this way. So what we get for the displacement? Un plus 2 minus un plus 1 for F1 prime. For F2 prime, un plus 1 minus un. So we just put the same, f1 prime will be this, f2 prime will be this. Hope you get it how we did this. Now f prime total force on the capital M mass will be this. Okay, now we get these expression. Force on small m was this, force on the capital M was this. So we have two equation of motion for these particles. For the nth particle, we have this equation m. This is nothing but acceleration because un is displacement. So we'll get this type of form. For f prime, we'll get this type of form. Now we need to solve, and we will solve the same way as we did in the previous one. Now we are having for the 2. So there are two ways to solve this, either to find a solution direct, and the second one is by assuming solution. So how we are assuming them like this, I already told you. Okay, so we take the solution like un equal to a e to the power I omega t minus kx hota hai. So at the place of x we write na because n it at the place of, like, displacement from here is a, 2a, 3a. For nth one that will be na, that's why we write it kna here. And for n plus 1 we have capital M particle. So the displacement will be different. Now if the mass is different of two particles, then the displacement or the maximum amplitude will be different for both the particles. So un plus 1 will be b e to the power I omega t minus k n plus 1a, because it is at n plus 1 location. Now for n minus 1, here is n, here n minus 1 is again capital M. So amplitude will be same for this. It will be v, b, and we'll add this equation. For n plus 2, n plus 1, n plus 2 again is small m. So we'll get the amplitude a e to the power I omega t minus k n plus 2a. Now we can write this equation in the form of this, because we can write it omega t minus k na, and we can take out ka. So it will be like this, and this will be like this. Okay, so now just substitute them in these equations, the 1 and 2. So what we'll get? We'll get these two equations. Means this term will be cancelled out, will take in common. This will cancel out, and when you just differentiate it twice, you will get what you will get omega square a m. So we'll get this type of equation, and from the second one you will get this type of equation. Okay, so these two equations you will get. Now try to solve the same way as we did in the previous one. You will get these, and we did nothing but just substitute all the un plus 1, un minus 1 in these values. Okay, and we found these two equations. Now what we will do, minus 2a plus, we take b common and divide by 2 and multiply by 2 as we did in the previous one, and e to the power minus ka plus e to the power I ka divided by 2 will be cos ka, like this. So we can write this equation this way, and this equation will be this way. Here we take the a common and divide by 2, multiply 2, so it will give us cos ka. So now we have this equal to this equal to this. So you will take out the a term here, minus 2 beta a here, and you will take a common. So minus m omega square and 2 beta will be there, a common, and you will take the b term one side. You will rearrange this equation, this and this, this and this, in the form of a and b. So it will be 2 beta cos ka b, because beta is here, so you will get something like this. And from the second one you will get something like this in the terms of a and b. Now you need to find the solution, you need to find the a and b. So how you can find? So it will form like a matrix, means you can write ab in this way, and you will write the four terms that are those, this and this. This will be in one matrix, and a or b will be in the second matrix, equal to 0. So a and b can't be 0, so this matrix should be 0. So this determinant will be this multiply this minus this multiply this. This will give us this equal to 0. So you all can solve the determinant. Now just multiply. So we get this type of something equation. Now from here we take the 4 common and make it 0. Then we divide whole the equation by small m capital M. So we'll get here a small m downside in the denominator. Here you will get the capital M. So from here you can take the 2 beta omega square common. You will get something like this, and it will be like beta square. So this will be here. Now cos square ka can be written as 1 minus sin square ka. So it will give us minus 4 beta square and plus 4 beta square, that will cancel out, and you will get something like this. Omega square square will came out this side, will cancel out, so we'll get something like this. So it is nothing but a quadratic equation in terms of omega square, that is x square x and 0. So from here you can find the omega square just using the formula minus b plus minus root b square minus 4ac divided by 2a. So omega square equal to this. From here we just substitute the values, that is minus b plus minus root b square minus 4ac divided by 2a. Now take the 4 common and 2 will cancel out from here, you will get something like this. So we get the two equations or the two roots, that are omega square equal to this, omega square equal to this. This one we called optical branch, this one we called acoustical branch. Okay, so these are the actual dispersion relations. Now these what we did today is just mathematical. In the tomorrow lecture or the next lecture, the 17 one, we will see how they are physically important or the significance of these equations in the physics. Okay, we will end today's lecture here. Thank you.